Hello, everyone. My name is Fu Wang, and I am an engineer at PayPal. And as we all know, Spark is a powerful engine for large-scale data processing, and which has already been adopted in a lot of companies. And but in some realistic production environment, there might be a lot of challenges that we may face to run a Spark application smoothly and efficiently. Today, I am here to share you my learnings of using Spark inside PayPal. And I'm also here to discuss with you all and learn from you all. Yeah, this is today's agenda. We have a very simple agenda. Firstly, I will introduce the challenges we are facing and how we resolve the problems in the production environment, and also share our learnings from the practice as well. Yeah, let's go to the challenges first. Basically, we have two challenges. The first one is the large graph with the data skew in nature. We have a huge graph in our production, and it has more than 2 billion vertices and more than 100 billion edges. And the degree of the load in the graph is different. The maximum degree of the load can reach 2 million. And meanwhile, the average degree is just 110. As you can see, the data skew exists here. It is in nature. And another challenge we are facing is the strict SLA requirement. And we have various limitations in the production. We have limited resources. I think some of you may have similar experience as me. Just sometimes we ask for the resource from platform team, and they usually push back our initial request and reduce the amount of our ask. And I think I can fully understand from the perspective, from the platform team perspective, but from our perspective, we need to balance the performance and the resource very well to meet our strict SLA. And that is the work we need to do. Basically, we have two paths. One is about how to improve our scalability, and other is about the performance optimization and enhancement. And firstly, let's go to the scalability part. The optimization is an old topic. We always like to talk about how to optimize our application, optimize our performance, reducing our execution time. But in many scenarios, actually, the basic and the fundamental requirement is to finish your computation and get the result. And but in many cases, our application cannot finish when the data volume increases and become huge. It may crash in the long term. It may run into out of memory issue. In other words, the scalability of the application is not good. Here, I would like to share one case in which we will improve our scalability of our application. In our graph product, as you can see at the side, as you can see in the picture at the right side, we provide the user with the capabilities of detecting communities and digging out some community patterns. And this capabilities can help our users to do a lot of analysis work, such as for risk control, for compliance management. For the community detection, there are a lot of algorithms that we can use, but and the connected component is one of them, and it is a very simple one. It's also a very commonly used one. I think some of you may have some experience of using it in your graph computation as well. And here I would like to take an example to illustrate how is the connected component is generated. By the way, we refer to this paper for the implementation algorithm of the connected component. If you are interested, you can take a look. Here you can see the simple undirected graph all the nodes in the graph is connected with each other directly or indirectly. So they belongs to a single connected component. Yeah, and then we can find one connected component, and we will pick the smallest node, which is node 1 here, as the representative node of this graph. And then we will get one community. We will get this new pairs of the community. All the nodes belongs to the community 1. Okay, here is some sample illustration. This is the input pairs. And next step is to make it directly, and then we will get a new pairs. And next step is to group by it by starting those. And then we will get a new pairs, a new aggregated RDD. Yeah. As you can see, we have different groups. In each group, we have a list of values corresponding to the key. And then we will find the smallest node in each group and linking all the nodes to the smallest node in each group. And then we will generate the new pairs. And then we will do the deduplication. We will do the dedupe to get a new pairs. And this is after this iteration, we will get our intermediate graph. And we will, after this iteration, we will go to next iteration and take the iteration of take the output of previous iteration as the input of the new iteration, and go through all the same steps, just like I introduced before. Just group by starting nodes, and again you get the group by aggregated and find the smallest node in each group and generate new pairs. And then we will get another intermediate graph. Yes. Okay, next we will go to next iteration. Iteration 3. Yes, and we will go through the same steps. And finally, yeah, we will go through all the same steps and generate the new pairs. And finally, we will find one community here, as the representative node of this community is 1, and the members are 1, 2, 3, 4, 5, and 6. And 10, the algorithm will just finish. We've already found one connective component. But now, where is the problem? Where's the problem happen? Yeah. As in our production case, in one single connected component, there might be more than 15 million nodes. It means in the group by step, for a single key, there will be millions of values. And since in the original implementation of our algorithm, we keep all the values in memory, so it results in the out of memory issue. We can say their skew happened in the group by step, and the out of memory happened as well. And okay, next let's introduce our approach to resolve this problem. Basically, we did 3 things to resolve the problem. The first one is separate the keys into normal keys and huge keys. We have set a threshold for this. And next, the second one is splitting the huge keys into multiple paths. By doing so, we by adding the number as prefix of the key. By doing so, we can increase the parallelism. And the third one is to split to disk in the reduced side when necessary to avoid the out of memory issue. By these doing things, we can resolve the out of memory and the skew problem in our production and finish the algorithm smoothly. Okay, here's some lesson learned of the scalability use case. Just 2 points I want to highlight. First one is do not blame Spark when you see out of memory, because from my experience, I have never seen out of memory issue, which is caused by Spark mechanism itself. In Spark internal, it will spare the data into disk when to avoid out of memory issue. So usually our out of memory issue is due to the inappropriate memory usage in our own use code. So making our memory usage in use code elegantly is the key to solve the out of memory issue. And the second point I want to say is the data skew is always exist, especially in graph data. They are in nature. We cannot avoid it, but the scalability can still be achieved by different solutions. For example, what we did here is split a huge key and spare to disk when necessary. The scalability can still be achieved by various kinds of solutions. Okay, let's go to the optimization and enhancement part. Before I go to the optimization part, I want to say there are a lot of common optimization tips which has already been shared in the Spark community. For example, we can choose different kinds of Spark configurations to make our application run faster. But I will not include those details here today. I just want to share one case here to illustrate how we optimize our application with help of understanding the Spark internal deeply. The first case is related to join selection strategy in the Spark planner. As we all know, Spark has different join solution for the join operator. Please allow me to quickly recap the three join solutions supported by Spark. First one is broadcast join. It can avoid the shuffle process. The second one is the hash join. Hash join the shuffle is necessary, but it will build local hash map for smaller set in the reducer side. And the third one is the summer join. It also needs shuffle, and it will sort both partitions of the table, both partitions in the reducer side, and tend to the merge to get the result. And at the right side is the workflow that Spark will follow to decide which join solution to execute. Firstly, it will check whether there is some hint in the circle statement that indicates the broadcast join. If there is, it will go to broadcast join. Otherwise, it will go check the data size of both tables to see whether it is suitable for broadcast join. If it is, it will go to the broadcast join. Otherwise, it will go check further conditions to choose from the hash join and the summer join. In our production environment, we have some join circles like this. For example, we have table A, table B, both of which are extra large table. And table B has a lot of partitions, and we just use one specific partition here. And this partition has a small data size, maybe just 1 megabytes. As you can see, actually this is a join between an extra large table before a small partition. But what join solution will Spark choose for execution? What's your answer? I think maybe many of you will choose the broadcast join just as I did. But the reality is broadcast join is expected, but the summer join is selected for execution. I think all of you want to know why. Let's try to illustrate this. Yeah, firstly, we have a circle string. We will go through Spark will use the parser to pass the string to get an unresolved logic plan. And then it will use the analyzer to resolve the logic plan to get a new resolved logic plan. As you can see, the unresolved relation A and B is resolved to have table relation A. And then the Spark optimizer will be applied to the logic plan tree, and the filter will be pushed down closer to the have table B. As you can see, both the have table relation A and B has a statistic item which is called size in bytes, and both of them are 1 gigabytes. After that, it will go through the Spark strategies, including the join selection. It will go through the Spark strategies, including join selection, and then the submerge join will be selected because the 1 gigabyte is not small enough for hash join and broadcast join. So it will choose the submerge join for execution. Here's our approach to enable broadcast join. Let's see what we change here. Yeah, here is the string, circle string. It will go to parser, and next one we will get the logic plan tree, and next 2 steps are same. We will go through the analyzer and the optimizer. Yeah, okay, please stop here. What we change here is add a rule which is called prune have table partitions in the Spark optimizer. What this rule do is to prune the partitions and update the size in bytes statistic item in the optimization phase, and then we will get the optimized logic plan tree. As you can see here, the statistic of the table of the have table relation B is updated to 1 megabytes because 1 gigabyte is the whole data size of the table B. Meanwhile, the partitions we are using is just 1 megabytes. So here our rule will correct the statistic to 1 megabyte, and then we will go through the Spark strategies. In the join selection, we'll select the broadcast join for execution because the 1 megabyte is good enough for broadcast join. Yes, this is our change and solution to enable the broadcast join. By the way, we raised a pull request for this change, and which is currently in Spark 3.0. If you are interested, just take a look, please. Thank you. Okay, let's go to another case. This is about one enhancement in our protection. This case is related to inserting data frame into have table. Just like you can see at left side of this slide, here's the DDL of the have table. We have 7 columns and 2 partition columns, and at the right side is the code in our Spark application to use the data frame. Firstly, we will new a data frame df1 from AddLogic, maybe which is complicated, and then we will register this data frame as temp table. After that, we will run a select query against this temp table. And here you can see we will rename the columns in the data frame to the columns to the corresponding column names of the have table to make sure the other column names matches. And then we will use the data frame writer dot insert into method to insert the data into have table. However, after this code run in our production, the platform alerts generated for us, and the platform team just come to us and kill our application. You know, this is very serious. Yeah, it's not a good thing. What is the reason? Because in this case, the adjust column of the data frame has been mismatched to the country column. As you can see, they are in different order. So this mismatch happened when the data is inserted into the Hive table. And the control column in Hive table is a partitioned column. The control column just have about around 200 distinct values. So just around 200 partitions created. But the adjust column has more than 10 million distinct values. So tons of new folders and files were generated or created in the HDFS, and which overload our name node service and impact some other applications. And so the platform team just come to us to care the application. Yeah, I think I'm not sure whether some of you have similar experience when the platform team come to you, and it's not a good thing, and we need to keep our reputation, right? If such problem often happens, then maybe when we ask for resource next time, the platform team will just reject us. So in order to avoid such problem happen going forward, we did some refinement in the Spark API to make our developers avoid such problem. As you can see, the DDL is same, and in the code, as you can see, one parameter is added in the data frame writer dot inserting into API. Yeah, we refined this inserting into API a little bit by adding a by name parameter. If the parameter is true, the Spark will do, firstly, it will match the columns between the data frame and the target table by name instead of order, which can resolve the problem we mentioned here. And then, if we write some incorrect column name in our code, it will also throw exception to remind our developer to correct the column names. So by doing so, our developers can pay attention to the potential mismatching and do the validation and then correct our code if necessary. So we have never seen a similar issue after we did this enhancement in our own Spark version, which is running in our production environment. Here's our lesson learned of optimization and the enhancement part. First thing I want to say is to meet our strict SLA requirement, nothing is too tiny to optimize our performance. We are willing to do anything to optimize our application. And during this process, I feel that it is really, really helpful for a Spark application developer to understand deeply in the Spark internals. It is very helpful for the Spark optimization and also for the enhancement. Just a tiny misusage may lead to very serious impact in some shared service, like the name node we mentioned here. So we should be careful, and sometimes explicit interface can help us, can remind us of such misusage, and then we can avoid this, just like we did here. And overall, with the continuously performance tuning and enhancement, our performance of the performance of our application has been improved by 4 to 5 times. Finally, here's a learning summary. From our practice of the real case in production, in conclusion, we want to share 2 points here. First one is use memory elegantly. As I mentioned, most out of memory issue is due to our own inappropriate memory usage in our code. It's not the fault of Spark. So we need to use our memory in our use code elegantly to avoid out of memory, to improve the scalability of our application. And the second one is really helpful to understand the Spark internal, to understand how it behavior underlying. It is really helpful to avoid the issues. It is also helpful the optimization of our application. And finally, I want to say after continuous tuning, we achieved the performance improvement from 2 days to around 10 days. But what I want to say is the number is not important here. The most valuable thing is the learning from our practice. And also I would like to discuss with you or to share the learnings of my experience. And I would like to discuss with you all and also learn from you all. Thank you.